functions of biological macromolecules using MD simulation approaches. So, as I have been directed that I have to talk about the MD simulations using Bromax. So, I will not take that much time. First of all, we would understand what is molecular simulation, what is MD simulation, what is molecular dynamics, right? So, as you know that the biological information flow from sequence to structure and dynamics. So, alternate word we can use here for dynamics is the function. So, basically, biological information flows from sequence to structure to dynamics. That means function of the molecules. So, sequence we know sequence means the combination or composition of biomolecules. Suppose we say we talk about the nucleotide sequences. That means how that particular nucleotide, that means DNA or RNA, that is made up of. Suppose we say about proteins, then sequence means composition of that particular protein, how the different amino acids are composed and they form a polymer known as polypeptides or proteins. So sequence means composition of the molecules, how it is made up of, and structure means how the molecule look like, what is the physical appearance of the molecule, that is known as the structure of the molecule. So we know that there are several techniques by which we can solve the structure of any biomolecules like X-ray crystallography or NMR or cryo-electron microscopy. There are many experimental methods that can be used to derive the structure of any biomolecules. Or in absence of any experimental techniques, we can also go for computational modeling. I think all of you are aware about the modeling methods, homology modeling or threading or de novo modeling, by which you can get the structure of the molecules. So this is how the static structure of any protein look like. So in this case, when we talk about the structure of a protein, that means we only have the coordinates, we only have the atoms present in the entire protein. They can be categorized into different amino acids, and then their coordinates in the 3D system: x coordinate, y coordinate, and z coordinate. So when you explore any PDF files, you can get all these things about that particular structure of a protein. That structure can give us an idea how the protein has been folded, what are the different type of binding sites are present in that particular protein, how the overall behavior of the protein, biophysical behavior, like how the charge distribution have been taking place in the surface of the proteins, the cavity that is favorable for which type of binding of which type of molecules, etc. So we can get the basic idea of what type of that protein can be. We can classify the proteins on the basis of their 3D structures. But if you want to know what will be the functions, I mean what will be the behavior of that particular protein in different conditions, what will be the behavior of any interactions when any protein binds to any ligand or any other metabolites, that can be studied only by molecular simulations. So here you can see the picture depicts the dynamics of interactions. So you can see here the protein is bound with some ligand, and you can study the behavior of these interactions in a reference of time. This is called as dynamics. So basically, computer simulation means generating an artificial environment or simulated environment using the computer, where we can study the behavior of the biological macromolecules. That is called as MD simulations of macromolecules. Next, why should we perform the dynamics? As you know that the experimental methods are limited and expensive. In that case, the molecular simulation process can complement the experiments. Like suppose there are many phenomena inside the cell that takes place in very small fraction of times. Many scenario, like you can see enzymatic activities, or some in some cases any photon transfer, any energy related phenomena that takes place in the cells through the biomolecules. They span for a very small amount of time. So in those cases we cannot find it out how the things are happening, what is the mechanism behind any biological phenomena, that cannot be traced out by any experimental methods. So in those cases we can use the molecular simulation to get the details about those phenomena. Second, molecular modeling is more concerned about the description of the molecule. That means uh, what are the atoms and how the atoms are actually interacting in the molecule. So molecular model that we see as a crystal structure or any computationally model structure, that is a static picture of any biomolecule. We can have just an idea about that molecule, but simulation is more concerned about the dynamics of the model. That means we can say here that simulation means kind of studying the behavior or studying a phenomena over the time, studying a process over the time. So you can differentiate in this way, like molecular modeling is just about generating an abstract of a real world entity. Like suppose you want just you want to generate an abstract in the computer system that can represent a real world entity, that is called as the model, or through modeling you get that particular model. But simulation means you are creating the abstract of a process. How processes are different from molecules? Molecules are just an object. Process means you are studying the behavior of that particular object over the time. So here you try to connect the macroscopic and microscopic behavior of that particular molecule through the theory of statistical mechanics. So macroscopic property that we are talking about, the thermodynamic macroscopic property like temperature, pressure, density, etc. And microscopic means that we already have, like atoms, their interactions, charges of every atoms. These are the microscopic properties. So basically here we try to correlate between these microscopic and macroscopic and microscopic world. Even for the very complex systems, simulations can be easier nowadays, and simulations require high performing computers. So here is a brief introduction about MD simulations. It's a computer simulation technique which calculates the time evolution of interacting atoms in a molecular assembly. Whether you take any single protein or you take any protein ligand complex, what you get is interactions among the atoms present in that molecule or present in that complex and their behavior. I mean, evolution of the interactions. How, for how much time span that interaction actually takes place, how the evolution of that particular interactions is actually happening, that you can study through interactions, sorry, molecular dynamic simulations. So there are different methods to study the dynamics of any biomolecule. One is the quantum mechanical study, and that is classical molecular mechanics, and third one is mixed quantum classical mechanics. So basically in the quantum mechanics, we represent the system, or we represent the atoms of any macromolecule using the wave functions presented by Schrodinger. That means we define the positions of all the electrons or other subatomic particles in the atoms, and we study the behavior of the atom in terms of the behavior of subatomic particles. But it is very much computationally expensive but highly accurate. Second one is classical molecular mechanics, where we limit many things. We reduce the system into an extent. We can say that here we use the Newtonian's mechanics method to study the behavior of the molecule. So here basically you will find that for every atom we only consider a single position. That means for every atom you will get only one position. That means described in three coordinates, and that is treated as the nucleus as well as the entire atom. So here we use the Newtonian mechanics. It is comparatively less accurate, but it can give you the results in a very small time. So it's faster in comparison to the quantum mechanical calculations. And third one is the mixed quantum classical mechanics, where we use most of the part of our system. We describe most of the part of our system using classical molecular mechanics, and some important part as quantum mechanics. So basically, when we study for any transfer of functional groups between the proteins and substrates, enzymes and substrates, proteins and ligands, or we study the behavior of photon transfer, energy transfer. In those cases, we can simply define a few amino acids as quantum mechanical calculations. quantum mechanical representation, and rest of the proteins can be represented using molecular mechanics. So MD simulation is more concerned about the thermodynamics of the system. So we will focus more about the classical molecular mechanics in this session, because as we know that implementing the uh, quantum mechanics is really very hard, and it requires high performing computers to perform. So it's better to learn the MD simulations from the classical molecular mechanics point of view, so which is based on the Newtonian's dynamics or Newtonian's molecular mechanics methods. And here actually what we do, we try to determine the net force working on a atom, and then working on the entire molecule, and accelerations that is experienced by each atom. This is the fundamental of Newtonian dynamics or classical molecular mechanics system. So at the beginning we have a system means we have a molecule that is our uh, study, and we want to study the behavior of that particular molecule. That molecule can be a protein or any other biomolecules, and that is present in an environment. That means it's a natural environment, whether it is aqueous or any membrane or something like that. So you have to generate that molecule with its own environment, and also you have to apply all the thermodynamics as the mathematical parameters. So here we study the force and acceleration that is experienced by each atom. So when we develop a system may contain everything. System will contain the protein molecule. System will contain the surrounding waters, different types of ions and everything. There should be every type of different type of molecules present in the system. Then we'll study the force and acceleration. So force can be further converted to energy, and acceleration that can be calculated from the displacement of the atoms. So at the beginning we have the positions and identification of all the atoms. We have all the positions of all the atoms I, and where positions are r, and we also have the mass of that atom, and we also have the partial charge, fixed charge of that particular atom. So these are the beginning, these are the basic things, or you can say these are the inputs for performing the MD simulations. So the Newtonian classical mechanics method tries to find the force experienced by that atom using this formula F equal to ma, which has been derived from the second law of Newton, and that can be simply expressed in this way: m equal to dv by dt, total change rate of change of velocity over time, and again velocity can be expressed in terms of displacement. So we study the displacement experienced by each atom, and from its mass we try to calculate the acceleration, and then we get the force. So I'm skipping this thing. It's not that much important. So what are the common forces present in any molecules? So mainly there are two types of forces that work in the molecules. One is the mechanical force or bonded force, which comes from the bonds, angles, and dihedrals. We already have idea about what are bonds and what are angles and what are dihedrals. Bonds means when two atoms form any covalent bond. So here bond means always the covalent bond. We do not focus on any non-covalent or weaker bonds. We only focus on the covalent bonds. In case of proteins, the covalent bonds are basically the peptide bonds, and the other bonds in the present in the um, side chain atoms, and also between C alpha and C atoms, and C and oxygen atoms. These are the covalent bonds. And angles means the angles formed between two different type of bonds sharing a common point, that is an atom. And all these things, bonds, angles, and dihedrals, they are actually uh, present in the proteins, and they are actually not fixed. When we deal with any static structure, we can see that bond angles, bond distance, angle between the three atoms, and the dihedrals, which is the angle between two planes, they are fixed. In case of static structure, they are fixed, but in nature the molecules are not fixed. They always try to at attain a zigzag position. They always dance like this. Bonds act as springs, angles they can extend in this way, and dihedral also move in this direction. Actually, it's not 360 rotation takes place for dihedrals. It can rotate in 360 degrees, but in both the direction. That means 180 one in one directions. Then some non-bond interactions also play important roles in the molecules, and these are electrostatic interactions and then van der Waals forces. These are also important non-bonded interactions present in the proteins. So this is the potential functions that is required for the MD simulations. So total energy is calculated from all these parameters like from bond energy, angle energy, dihedral, van der Waals, and electrostatic. So bond energy can be calculated from this formula, as we know that this is the formula. Bond energy is basically to find an ideal position between two atoms when the energy is very much low. So one one bond distance we get from the static structure, input structure. One is the ideal bond distance like b0, and kb I is the bond dissociation constant. So this is the formula for the getting the bond energy potential. Similarly, we can generate the angle energy potentials, van der Waals potential, dihedral potential, and electrostatic potentials. Now, one important thing that is needed for performing the MD simulation, that is the force field. So we should understand the concept of force field first. So basically, while performing the MD simulations, the molecules that we take as input that are described as series of charged points and springs. Charge point means the points represent the atoms, and springs are just nothing but the bonds. And the properties of the molecules are assigned by the force field function. So these things are not sufficient to study the behavior or study the interaction, study the dynamics of any molecule. We have to assign many more things. We have to assign many more potential functions to that to that molecule. Then only we can study the dynamics of that molecule. So basically, only atoms, charge points, and bonds are not sufficient. We have to parameterize the molecule. That's why we apply the force field. Force field provides three things. One is the set of functional forms, set of equations that will be needed to calculate different type of parameters from that molecule, and then parameter for the functional forms. What will be the standard value, ideal value for any particular bond? What will be the ideal angle between three atoms? What will be the ideal dihedral between two different planes? So these are the parameters. These are already pre-assigned, that and that those are required for performing the MD simulations. So apart from these two things, another more thing required, that is the definition of the building blocks. Like suppose you are performing MD simulations with proteins, then there will be different amino acids. Many will be standard amino acids, many will be non-standard amino acids, some will be modified amino acids. So they will be described before you perform simulations. The system should understand that this is an amino acid and this is a molecule, this is something, this is that. Like this, it has to understand every molecular description. Okay, so that's why force field is used to define these things. Now, objectives and goal of the MD simulations. So these are the objectives. We can take a note, that is validation of validation of model structures. That means just after the homology modeling, if you want to validate the quality of the structure, if you want to refine that structure, you can go for the MD simulation. Basically, in the process of refinement, the errors present in the structures, they can be solved. They can be uh, the errors means basically steric clashes and hindrances, and they can be removed from the structure, so that the quality, overall quality of the structure will be improved. Second, understanding the properties of biomolecules, like any specific property you want to study, any specific function, any specific interactions that you want to know, then you can go for MD simulations. Protein folding, in case of some unfolded or partially folded proteins can be simulated, and then we can get the completely folded proteins. But for this particular purpose, uh, you may require to simulate the structure for a very longer time, because we know that protein folding takes place in microsecond of microsecond scale. And next is drug enzyme activity. If you want to study the interactions of drugs with the enzymes or proteins, and how the binding free energy or affinity of the enzyme for for that particular drug is actually increasing, and these things can be studied in MD simulations. And lastly, the chemical reactions, where any functional groups are taken, are actually transferred between the enzymes and substrates, or cofactors and substrates, not by enzyme remain isolate. And also enzyme catalysis, how it takes place, any reaction takes place, any group is transferred. These things can also be traced using MD simulations. So goal of MD simulation is these things. These are the macromolecular, macroscopic properties that we generate from the MD simulations. Like we study the molecular geometries and energies of the molecules. We study the mean atomic fluctuations, deviations, etc. We check the total configurational rates and conformational distributions. We study the free energy differences between different states. And also we focus on the interactions between the parts of the systems, like enzyme substrate binding. So these are the practical aspects of studying MD simulations, and objectives are the main purpose of performing MD simulations. So, in the MD simulations, we describe the biological systems, or you can say protein systems, in different ways. So, there are some common phenomena, common parameters associated with it. Like, suppose we try to describe our system in three terms. One is the number of molecules present in the system, total energy of the system, and total volume of the system. So, out of these three things, we have developed several ensembles which are required during the simulation process. So while performing the MD simulation, we have to bring these three things: number of molecules, energy, and volume, as constant. So when these three things are constant, that system can be called as microcanonical constant. That means system is in constant volume. And after that, we have to equilibrate the temperature. That means uh, in the first in the first stage of molecular simulation, we have to provide heat to the system, so that we can increase the temperature of the system. So when we apply the temperature to the system, the energy is increased, and when the energy is increased, the atoms acquire that energy and start to move. This is our desire. When atoms start to move, then they follow some rules, physiochemical rules, and on the basis of that, they just try to bring their positions. They orient, reorient, and finally they attain their stable and native states. So for this, we have to bring the temperature constant, bring the temperature of the system is constant, and that state is known as NVT, or constant temperature system. And in the third type of system, we try to bring both temperature and pressure as constant, along with number of atoms, volume, and energy. So this state is known as NPT state, NPT equilibrated state, and also known as isothermal and isobaric states. So this is the process and steps of MD simulation. We'll discuss about all these steps in details. First of all, I would like to mention some programs, softwares which are used for MD simulations, and few are mentioned here. The leading ones like Charm, Gromax, NAMD, Ember, and Desmond. And uh, there are some popular force fields, classical force fields, which are used in the process of simulation. These are also very much important. So while performing the MD simulation, you have to choose a proper software or program to perform the MD simulation, as well as you have to choose a proper force field, because force field actually parameterize the system. So if you choose the proper force field, then you can get a better result. Okay, so these are the steps for MD simulation. First one is the first one. First, you have the initial coordinate. Suppose you are just about to simulate a protein, then you just start with the PDB file of that particular protein. So start with the initial coordinate of that particular protein, and then you have to generate the topology. Topology generation means you have to convert the PDF file according to the format defined by the software. Suppose we use the Gromax for simulation. GROMACS is fast, free, and flexible. So first thing is you have to convert that PDF file into the GROMACS supported topology files, so that GROMACS can understand the all atoms used in the protein, all atoms present in the proteins, all bonds present in the proteins, or all angles and all, everything that is present in that PDF file, that can be understood by the GROMACS. And third step is box definition. In the box definition, we define a boundary. We set a boundary of the system so that we can set the number of atoms fixed throughout our simulation. Because one important thing is that if you do not set any boundary of the system, what will happen during the process of simulation, when we energize the system, when we put some temperature, increase the temperature, we put some heat, what actually happens, the atoms start to move. So in that cases the atoms will move away of the boundary. If you do not set in boundary, then boundary of the system will be very large, and calculating the energies, in calculating the interactions among the atoms will be very much difficult. That's why we should define the boundary in a proper way, so that we can consider that all the number of atoms should be fixed in the system. And second is that if you put any boundary, that also violates the rule of natural biological system. Because in the biological systems we know that there is no boundaries present, so atoms like waters can move from here to there. So to bring this both these things, like to bring the systems boundary, and also to bring the concepts of real world system, we apply a concept here that is known as periodic boundary condition. So by introducing the Fourier transform algorithm, we what we do is we just create infinite numbers of pseudo systems or false systems or imaginary systems throughout the real system. So what happens when one atom moves from one system and enters the another, correspondingly the atom from the neighboring system will enter to the original system, so that the number of atoms at any point that will be unchanged. And after defining the box, we have to go for the solvation method. That means we include the waters in the system. At the beginning, we had only protein. And when you set the boundary of the system, you should consider that the edge distance, minimum edge distance from the protein's surface to the edge of the system, that has to be a minimum 7 Armstrong, or it is always better that you should keep it 10 Armstrong away. Because what happens when one protein tries to move from one box to another, the simultaneously another protein move from another box to that system. So in these cases, if distance is very less, then what happens, uh, atoms from different boxes will try to interact, and the calculation will be very much wrong. That's why the edge distance is very much important to maintain. It has to be minimum 7 Armstrong, or if better you can put it you can keep it 10 Armstrong. And next, you have to neutralize the system charge. That means if you have any charged amino acids in the protein, then it may create some problems while performing the simulation. So ultimately you are not neutralizing the protein, but you are neutralizing the system. And then you have to perform the energy minimization, and energy minimization, that is a step that is followed even for refinement of the protein structures, and this is very much important before you start any molecular simulation, because at this step the common errors and problems of the protein structures are actually resolved. Then you have to go for the temperature equilibrium, where you try to bring the system with constant temperature. And after that you go for pressure equilibrium, where you try to bring the pressure of the system is constant. And then you go for the production run, which is actually the molecular dynamics of the system. So the production run will be the continuation of the pressure equilibrium. Actually, what happens in case of pressure equilibrium, we try to bring both pressure and temperature at constant. So after that, you can perform the MD simulation as a continuation of the equilibrium. And after the MD simulations, you can get the trajectory of your simulation. You can get the trajectory, means the path, the molecular evolution, or you can say the time dependent structural coordinates and energy along with the velocity can be stored, and that can be analyzed in different ways, and some common analysis are given here. what we do after simulation is we study the RMSD of the system, RMSD of the protein, which is known as the root mean square deviation. That means we try to find from one frame to another frame what is the overall differences in the structures of that particular protein. We also study the RMSF, which is the mean deviation experienced by each atom throughout the simulation. And then hydrogen bonds, number of hydrogen bonds can be calculated. Then you go for the free energy calculations, like in different states what is the difference in energy for a particular protein, or you can say before binding with any other molecule, before binding and after binding what is the difference in energy, that is called as the free energy. You can also go for studying the radius of gyration. That means the overall packing of the molecule. Radius of gyration represent the overall packing of the molecule. Then you can perform the PCA, principal component analysis, to study the direction of the dynamics. And then you can go for the solvent external surface area analysis, secondary structural analysis, radial distribution functions, dimensional plot. So these are the different type of analysis you can perform. So these are only a few or major analysis. There are also many more you can perform after you complete the MD simulation. So I was thinking to demonstrate you about all these things, but I'm little worried how I can show you, but I must show you few things how we perform the MD simulation. First of all, as I was directed to show you about Gromax, so you can simply search the websites of Gromax. MD simulations are best performed on the Linux devices, not Windows, because Linux, as we know, that Linux is more customizable, most stable type of operating system, and most of the high performance computing they use the Linux as their operating system, and that's why most of the simulation programs are developed for the Linux systems only. And Gromax is one of the very popular molecular dynamics program, and this is fast, free, and flexible. Uh, Time taken for simulation is very less. So this is the website of Gromax. So if you want to use the Gromax for your simulation work, then simply you should access this website. You can download the latest version of Gromax from here. You can simply click on the download link and you can download the Gromax and you can install in your system. For the installation, you can follow this introductory materials where it will tell you about not introductory material. You have to click on the documentation. Here there will be a complete guidance about installation of the Gromax. So these are the processes by following which you can install the Gromas in a system. First of all, it has some prerequisites like you should install the CMake in your system, and then you should download the Gromax. Then you should unpack the Gromax file. Then you should run the CMake command, and then make command, make check, and make install. So these are the steps you have to follow to install the Gromax. So first you download, then in your system this file will be created. Then you should move to this file. Then you should create a directory, then change the directory using the cd build. Then use the cmake command with these options so that Chromas will be configured. And after that you should use this command make, and then make sudo make install to install the Gromax. So after the installation you can use this command to access the Gromax source, then these things. So this is the default location where the Gromax is located or installed. So these are the ways you can follow to install the Gromax, or otherwise there is a simple method. You can simply use the command uh, sudo apt get install Gromax in your system. So by this command, the Gromax will automatically installed in your Linux system, whether you are using Ubuntu or Fedora or Red Hat, anything, and that will be installed in your system by using this simple single command. Okay, so once installed, then you should start with the mm, PDF files, and that will be your input to perform the MD simulations. So I would recommend there is another there is one website developed by Justin Lemkul and his team. I must recommend you this site to follow before you try to learn Gromax. So here you can find different systems. Tutorial of Gromax simulation, tutorial of MD simulations using Gromax using different systems. And you should always start with this lysozyme in water. It's a simple only protein will be there, and once you start learning from this system, you can also perform MD simulations using membrane system. You can study the protein ligand interactions. You can also study the van der Waals transformations. You can study the free energies. You can perform the umbrella sampling and many things you can also study. So you should always start with this lysozyme in water. So this tutorial gives a well documented, or you can say detailed description of learning Gromax. So I had prepared all the steps and all the files in between files that are required. So for now, I can just show you how to perform it because I cannot show you directly with demonstration. So in that case, I can only tell you what are the steps that are followed to run the Gromax. So first thing, you start with the PDF file that you download from the PDB database. Just like here, one file is given, one AKI. This is an example file that you can download from the RCSP PDB database. I think all of you are aware about this, aware about this RCSP PDB database, where from here we can download the structural files of any proteins or any biomolecules in the PDB format. Some other formats are also available like CIF that can also be downloaded and converted into PDF. So Gromax starts with the PDF file. So once you download the PDF file, what you have to do is you have to process that PDF file. Because when we download any PDF file, I will show you one thing. Suppose this is my PDF file. I have just downloaded from the PDB database. I'm showing you this file using PyMol. Now you can see this is a protein. All the atoms are arranged, and along with the proteins there are many dots are present, these red dots. These are the water molecules. Actually here dots represent a single atom. Basically these are the oxygen atoms. And you know that in the X-ray crystallography method we cannot capture the hydrogens in the system, in the molecules, unless the resolution is very high. So mostly in case of all the protein structures present in the PDB, you will not find any hydrogen atoms. So only oxygen atoms will be there as the water molecule. So first thing you have to remove all the crystal waters from your system, and you have to clean your system in such a way that there will not be any missing atoms in your PDF file. There will not be any incorrect nomenclature of atoms. If any such things occurs, then you have to rectify the initial structure first, then only you can go for the MD simulation. So first thing you have to clean your protein structures using this command. Here is simple command. Using the grep command you can clean your PDB structures. So this is your input file, and you have to search the lines of coordinates where HOH is written, and you have to remove them. So this is the command to delete the crystal waters from your PDB. So by this your protein will be cleaned from the crystal waters. But if your protein contains any uh, non uh, non-natural atoms, or you can say protein contains any atoms which are not very popular or not known to Gromax, or you can say there is any wrong nomenclature, that should be rectified in different ways. And second thing, if there are any missing atoms or missing residues in the structure, that has to be removed first, that has to be solved first. So this is the first step of performing MD simulation. And after that, you have to generate the topology of the molecule. So to generate the topology of the molecule, you should use this command. This is the command to run the topology of the molecule. So you can see here what we are doing. We are running this command pdb to gmx. This is the command. Along with this gmx, it will be run, and these are the flags of the commands like dash app, dash o. Dash app is for the input, because this is the first step of Grommas command, that is for topology generation. You should take that clean PDF file as input with this flag dash app, and dash o for the output file, and you should give a name for the output file generation. And then you have to use a water model. You have to select a water model. So by default, it is written as TIP3P. Otherwise, you can keep these things omit, or you can simply type the command without this water option. So when you don't mention any type of water model, what it does actually, it asks for a water model to select out of all the available options. So you can simply type this command, and then it will ask for selecting the water models. It will ask for selecting a force field. So Gromas already it has many pre-built force fields, and these are listed like this. You can see here by different numbers, different force fields are mentioned. So you have to choose your most favorable or most suited force fields before you go for the simulation. It's up to you which force field you will choose, or you can download any standard more advanced, more modified force fields from internet, and you can also use it for your own simulation. So after choosing a force field, it will ask you again these things like termination, how you treat the terminal amino acids of the proteins, like N terminal and C terminal. These things will be you have to solve. And if you have any interactive complexes, and that will also will be treated differently. So the on the basis of your input PDF file, you should follow a proper protocol to generate the topology. So once you successfully generate the topology, this command will create three files. One is topology file, that is known as something.top, that automatically named as topol.top, and two other files. One is position state file, and another is the coordinate file in Gromax format. So you can see here, this is the PDF file. This is nothing but the coordinate file in the PDF format. This is the coordinate file in Gromax format. So after topology generation, you can also get many things about the topology, how things are generated, what are the important uh, features of those files that you can see. That is already described here. It's a very well documented tutorial. uh, Many things that you may not understand what is happening during my simulation, what are the files generated, what are the different contents, what are their meanings, you can simply get it from here. So after topology generation, next step, you have to perform the solvation. So before you go for the solvation, you have to set the boundary. You have to define the box. So this is the command by which we set the box. Like suppose gmx edit conf is the command that to be followed to uh, generate the to define the box. And input file will be that processed grow file generated in during the topology generation. Dash f is the flag for taking the input of this file, and dash o is the same. Topology file will be generated, but at the end of the topology file there will be box definition in xyz coordinates will be mentioned. And some other flags are also used here, like c dash c is for putting the molecule at the center of the box. Dash d is for the distance, edge distance, and that is mentioned as 1.2 nanometer. So I told you that to keep at least 7 angstrom or zero point 0.7 nanometer. But for a good simulation, you can set this distance, that is 1.2 nanometer or 12 angstrom. BT means the box type, and that is cubic. So you know that different type of box can be created during the simulation. It can be triclinic or dodecahedron. Many options are there on the basis of the shape of your molecule, shape of your protein. You can set a particular box, but cubic is a more popular one. But it can be implemented easily. But the drawback is that when you use the cubic system, it always accumulates more water. More water means more atom, so more calculation. It will require more time to perform. So this is how you define the box. Then next step is to solve the system. So you have already selected the water models that to be used. Now you have to follow this command gmx solved, and this command will fill the box with water molecules. And I will show you step by step how it actually looks. Taking long time. Yeah. This is my initial file that I had created after the topology generation. I think you can see it. This is the initial molecule. And after that, I had defined the boxes. I'll show you how after the box definition, how the molecule actually looks like. Same super. I can see the box that is defined by the command edit conf. And after the box generation, I have solvated the system. So after the solvation, you can see what happens to the system. Solve.grow. So after the solvation, the system looks like this. You can see here the protein is there in the center, at the center of the box, and the system is filled with water. I'm showing you the molecule separately. First one, I select the protein only, and I am changing the method of drawing, that is new cartoon. Coloring method, I'm using secondary structure, so you can see the protein distinctively. So this is the protein and filled with water. So after the solvation, the system looks like this. So after the solvation, next step is you should go for the adding ions, because after the solvation you can check your system may contain some charge. It can be positive charge or negative charge that comes from the total sum of charge provided by the charged amino acids of proteins. So here you can check the charge of the system using this command. This command can give you the charge of the system. So to run this command, you should have one input file known as ions.mdp file that you can download from here. This is the ion.mdp file that can be used to find the charge of the system. So I'm not describing the details of this file for now. So you should use it as input file. Flag will be like this: dash f, then mdp file, then dash c, then give the input file after solvation, and then dash p, and the tuple dot top, and dash o ion.appear. So this file will be generated. It will use this file, and this file. So this is already prepared in our system while we perform the topology generation. So using this command, you can find it out how many charge is there in your system. Then to neutralize the system, neutralize the charge of the system, you can use this command gmx genion. So you already have successfully prepared this file. Then just take this file as input using this command dash s, and then dash o will be the output file that will contain the ions to neutralize the charge. And for neutralizing the system, we use this sodium ion and chlorine ion in to make the system neutral. These are the commands you have to follow thoroughly. And second thing is that when you add some ions to the system, you have to remove some atoms from the system also. So for that purpose, we always select solution or solvent to remove. So when we add some ions, we have to remove some solvent atoms from the system. So you can read these things in details if you want to learn all the things, if you want to know all the things. So after ion addition, the system may look like this. Next step is energy minimization, where you try to minimize the energy of the system. And for this, again, we have to deal with one MDP file. That MDP file can be downloaded from here. This is the MDP file. MDP means MD parameter file, molecular dynamics parameter files. So this is the MDP files for energy minimization. You can see different options are given here. Number of steps we mentioned. So there are two stopping criteria when the system's energy minimized thoroughly. Stopping criteria one is the steps when the system completes this number of steps or this number of cycles of minimization, it will automatically terminate. Otherwise, when the total force of the system that will be less than 1000 kilojoule per mole per nanometer area, then it will be minimized. So this is the first command to perform the minimization. It generates one tpr file. TPR file that contains everything. It contains the topology, it contains the parameter, it contains everything. So this is the TPR file generated, and then you have to perform the md run command. Md run command is actually used for the md simulation. So this will be the command for energy minimization. And by default, all the outputs will be produced by this name em. So after the energy minimization, when it terminates, it will create several files. One of them is em.edr. This is the energy file, binary energy file. These are the four files will be created after the energy minimization. em.log that describes about the steps of energy minimization. At every step, what was the energy and how it was reduced. And then trr file is the trajectory file. It's not required for now. Grow file is the output file, coded file produced after the energy minimization. And edr file is the energy file, binary energy file. So you can see the total energy after the minimization. And then if you want to plot the energy of the system, so basically here till now we have not applied any heat to the system, we have not applied any kinetics of the system. So you will get only potential energy of the system. So if you plot the total amount of energy versus the frames in how many cycles the energy was reduced, so it may look like this. So at the beginning the energy was very high, and during the process of minimization you can see after 100 steps the energy lowered to this point, after 200 this point, just like this it becomes stagnant. So if you find such kind of graph, then your minimization process has been successfully completed. And this type of graph can be generated using this tool, xgrams. uh, you can install it using normal command, sudo apt-get install xmgrace, and not xmgrace only grace, then it will be installed. And then just type this command. First you have to use this command gmx energy, then dash f eme.edr, then dash o potential.xbg. It will generate this file potential.xbg. Then you should use this command xmgrace potential.xbg. It will show you such kind of graph. Everything is written very in details here. So after the energy minimization, you can go for the equilibration, where we perform the equilibration of the system in two steps. First step is temperature equilibration, and second one is the temperature and pressure equilibration. So again, we require the MDP files for the temperature equilibrium. You can download it from here. This is the MDP file for temperature. Sorry, temperature equilibrium. So one thing to remember that here we use some constraints, because when you apply the heat to the system, suddenly they attain their kinetic energy and they try to move. So when we perform the temperature equilibrium, what we do is we try to fix the positions of the heavy atoms, all the heavy atoms of the system, so that they do not easily move. And these position states are actually attained by applying a force constraint for all the atoms, all the heavy atoms present in the proteins. And this constraint file is actually created during the process of topology generation. And some parameters that to be considered here, these are important. The number of steps that you use for equilibration, and the output that will be saved, the difference of times and intervals of times, everything should be followed properly. And the different non-bounded parameters like cutoff schemes, uh, ns type, ns list, van der Waals parameters, everything should be carefully set, or for by default you can uh, use this MDB file for your simulation. It's kind of verified and tested. And here you can check one thing. We are bringing the temperature of the system at 290 degree, 298 degree Kelvin. So this is the standard temperature that can be used. It's actually room temperature that can be used for most of the protein simulations. So if your protein environment is something else, then you can set the temperature accordingly. So the system will try to bring the temperature of the system constant. That means it will try to bring the temperature of the system as 290 degree, 298 degree Kelvin. Rest you will understand later. At the beginning you cannot get all the things about the parameters. You should know step by step. So this is the first command for generating the tpr file of temperature equilibrium. Then you should run this command gmx md run, and this command is used for define the name. All the output files will be named as nvt. And after that you can check the energy of the system. After that you can check the temperature of the system. So everything is stored in the CDR file. Again, just like the EDR, here also you will get a file that is known as nvt.edr. Actually, same number of files are generated after the temperature equilibrium. One EDR file, one log file, one trajectory file, one grow file, topology file. So you can check the temperature, how it has been stabilized. It will look like this. And after that you should go for the pressure equilibrium, where again you may require another mdp file. You can download it from here. So one thing is that after performing the temperature equilibrium, you should keep the continuation ES in the MDP file. So this is the MDP file, because temperature and pressure equilibrium are not isolated steps; they are interdependent steps. So here you can see continuation equal to ES, but in case of temperature equilibrium, continuation is mentioned as no. So here after the temperature equilibrium, we are performing the pressure equilibrium. So it's process of continuation. and you will not find that much difference from the temperature equilibrium file. One additional thing, pressure coupling is on, so these parameters are mostly absent in case of temperature or NVT equilibrium, but in case of pressure equilibrium you will find these things, because we don't consider anything about pressure in case of temperature equilibrium. And here we not only perform the pressure equilibrium, but also we focus on the temperature equilibrium. So the parameters we set on the temperature equilibrium, that will also be set here. And then you should perform the pressure equilibrium, and using this command mdrun, define them npt, and all the output files, just like this edr file, one uh, trajectory file, trr file, grow file, and another one is log file. Same file, number of files will be created, and again you can check whether the temperature and pressure, whether it has been equilibrated or not by using this same command. First generate this pressure.xbg file using this command, and then select the pressure by typing 17, and then this file will be created, and then type the command xmgrace pressure.xbg. It will show this type of graph. You can also check the density of the system by using this command, and for again for density, to get the density you should select 23 using the same command. Same command will be utilized like gmx energy dash f npt.edr. Just like here we have used gmx energy dash f npt.edr dash o, then give the name of the new file. And then finally, the production MD. In the production MD, what we do is we actually continue the equilibration up to some time scale of simulation. This is the ultimate step of MD simulation. Again, for this, we may require another MDP file. This is the MD file of MD simulations. So here you can see that we have removed all the position restraint files that were earlier mentioned, and then rest of the parameters will be almost same as the pressure equilibrium, like npt dot mdp. You will not find that much change in this mdp files. And one more important thing is that here you mention the number of steps to be performed. So here you can see that this much number of steps are followed for 10 nanosecond of simulation. Not, it's not for 10 nanosecond actually. This is how much? It's 5 lakh, I think. Like 1, 2, 3, 4, 5, 50 lakhs. 50 lakh means 10 nanosecond of simulation. So if you want to perform some more time of simulation, like suppose you want to perform uh, uh, 50 nanosecond or 100 nanosecond or 1 microsecond, accordingly you can set this type of value. So simple calculation. And after that, you have to run this command jmsmd run and define name. You can give any name here. And once you complete all the steps, the simulation will be completed. And when simulation is completed, it will generate again grow file, trajectory file, and EDR file that stores different type of macroscopic parameters like temperature, pressure, density, etc., energy, everything. And here the trajectory file is important. The output of the production run is actually the trajectory file. And first step, before you go for any analysis, you should remove the periodicity from the trajectories. Periodicity means when we apply the periodic boundary condition during the process of simulation, it creates some. It actually the output of the simulation looks like broken, or atoms are jumping across the different sides of the box. So to remove all these things, we try to remove the periodicity of the system. So this is the command to remove the periodicity. That is gromax trjc1ab, and then use the tpr file generated before the MD simulation. Then use the XTC file, that is actually the trajectory file generated after the MD simulations, and then this will be output file without periodicity. So this file will be your important file. Further analysis will be performed using this file only. So different type of analysis we perform, like root mean square deviation, where perform we try to find the deviations from one frame to another, that gives us the result um, as an average deviations of all the atoms, average deviations taken from all the atoms. So for this, you can use this command gmx rms and then take this tpr file as input. So this is the starting file that we have generated before you perform the simulation. So this is the starting file. So it contains the coordinate of the uh, starting protein, not protein, starting system. And you can say this is kind of reference file, and with respect to this, what are changes occurred during the process of simulation that are stored in this xtc file. So you will find multiple frames in this particular file. So in comparison to this, with the reference to this, what is the uh, overall deviation of the structures that can be stored in this rmsd.xbc file. And you can choose different parameters like backbone or C alpha of the atoms to check overall deviation of those atoms together, how it actually looks like. And sometimes you can see this type of result. This is the overall deviation you can see. It may produce a graph like this. If this graph becomes plateau, that means the structure of the protein is actually stabilized. You can also go for the RMS RMSF calculations. You can also find the radius of gyration. The command will be a little different, and you can get all the commands from the GROMAS documentation site. Like GMX gyrate is used for finding the gyrations and study the radius of gyration. So this is the command again. Like this, you should take the input reference file, then trajectory file, then gyrate.xbg, and these are the basic syntaxes, common parameters to be followed. And if the gyration line look like this, that means the overall packing is good. If it increases, then the proteins gets unfolded during the simulation. If it becomes less or it just goes down, then it means that the protein gets more compacted. Just a second. So these are the common analysis we perform. Along with that, we can also perform the DSSP analysis, which gives us the idea about the overall evolution of the secondary structural elements. Evolution of the secondary structural elements, how they vary, how they change, like alpha helices, beta sheets, everything, how they vary throughout the simulation process that you can study. And number of hydrogen bonds, in intraatomic bonds or interatomic bonds, both can be calculated. Not only these things, many more calculations can be performed on the simulation. So these are the overview of the molecular dynamics simulations using GROMAX. So it would be, better if I would have performed it in Linux system, but I think it's not possible for now. Someday later, I can show you how to perform the simulation in details. Any question?
So these commands should be run in terminal or
Yes,
in.
yes. Everything should be run in terminal, and your initial file should be present in a folder. And from that folder only, you will open the terminal and run all the commands.
Okay, sir. So we cannot directly access the GROMAX tool.
Why can't you directly access? You have to install in a system. You should have Linux system only. If you are using any Linux system, then you will install the Gromax in your system, and you can start working. There will be
O-
no issue.
Okay, if there is no Linux, then we
And
can
then you
work.
can use the cloud-based system, or you can use any high-performing computing from any remote area. You can access the remote computers and you can work. But to learn, I think you should install the Bromax in your. You should install the Linux in your system, and you should learn the things that is a